Welcome back. In this video, you will learn how to find area under polar curves. Let's get to it. Alright, so in Calculus 1, you learned that you can calculate the area under a curve by using integration. And whenever we have calculated area under a curve, we have been doing that within the rectangular coordinate system, right? We would have some curve represented by y equals a function in terms of x, and we would want to calculate area beneath that curve between two specific values of x. In this case, I have them labeled with a and b. And in order to calculate that area beneath that curve between those two values of x, we would use the following definite integral. That area is equal to the integral from a to b of the function f of x that represents the curve times dx. And what this definite integral is doing in order to calculate this area underneath the curve is it's adding up the area of an infinite number of rectangles between these two values of x, a and b. All right, and you can see that visually here. Obviously, this is not an infinite number of rectangles, but I just have a couple drawn here so that you can see what I'm talking about. When we are integrating our function times dx, what we're actually doing here is adding up the area of an infinite number of rectangles where f of x represents the height of each rectangle and dx represents the width of each rectangle. And so you can see that up here. The height of each of these rectangles is dependent on the curve y equals f of x. So that's the height, and then dx represents the width of those rectangles where that width is getting infinitely small. Alright, so as that width dx gets infinitely small, you could see how we would get more and more rectangles between a and b to more accurately represent the area beneath this curve. Okay, so that was just a refresher. When we calculated area beneath the curve in the rectangular coordinate system, we integrated between two values of x for where we wanted to find the area beneath the curve, and we're integrating f of x dx, which represents adding up the area of an infinite number of rectangles. But what if we want to calculate the area underneath a polar curve in the polar coordinate system? How is this process going to compare to calculating area beneath a curve in the rectangular coordinate system? Well, if you take a look at this graph here, you can see that we have a polar curve represented by r equals a function in terms of theta, right? R equals f of theta. And we want to calculate this area right here that lies between two angles. All right, instead of calculating area between two values of x, like we do in the rectangular coordinate system, right? We want to calculate the area between a and b, which are two values of x. In the polar coordinate system, we're going to be calculating area between two angles of theta. Theta equals alpha and theta equals beta. All right, so we're calculating area between two angles beneath a curve from a lower angle to an upper angle. So in this case, when we want to calculate this area beneath a polar curve, we're still going to integrate, but instead of integrating between two values of x, a and b, we're going to be integrating between two values of theta, alpha and beta. So let's write that down. That's the first thing that we know about calculating the area beneath a polar curve. We're going to be integrating from some lower bound alpha, which is an angle of theta, to some upper bound beta, which is also an angle in terms of theta. All right, and so since our bounds of integration are going to be in terms of theta, that means that the rest of our integral should also be in terms of theta, right? In the rectangular coordinate system, we integrated between two values of x, and we integrated f of x dx. So in this integral that will represent the area beneath a polar curve, we should be working in terms of theta. And that makes sense, because if you look at our polar curve here, we have r equals some function in terms of theta. All right, and so what are the contents of our integral here actually going to be? Because in the rectangular coordinate system, the contents represented the area of a rectangle that we are adding up infinitely between our two values of x. But if you look at this graph, we don't have rectangles anymore, right? Between these two angles, we have what looks to be these triangular shapes, but they're actually not triangles, don't let that fool you. What they are sectors of a circle. And so if you don't remember what a sector is from geometry, essentially what a sector is just part of a circle that is made from an arc along the outside of the circle between two different radii. So for example, if I just draw a circle here real quick, if this is the center of the circle right here, if we draw two lines from the center to the outside of the circle, which would be the radius of the circle, this little shape that we just created here is what you would call a sector of this circle. It's formed by two radii and an arc of the circle. All right, and so that's essentially what we're working with here. We have several little sectors between these two angles of theta that make up the area underneath this curve. And so when we calculate the area beneath a polar curve, we're not going to be adding up the area of an infinite number of rectangles, we're going to be adding up the area of an infinite number of sectors. And the area of a sector of a circle can be calculated using the following formula. The area is equal to 1/2 times the radius squared times theta, as long as theta is measured in radians. All right, if it's measured in degrees, this area formula will look a little bit different, but if theta is in radians, then the area of a sector is represented by this formula. All right, so if you know what the radius of your circle is, that would be this measurement right here. This is the radius, and you know what the angle of your sector is. That would be this measurement. That's the angle theta, right? The angle from this radius to this radius would be our angle theta. If we know those two values, then we can calculate the area of a sector of a circle. So in this case, what would represent the radius and the angle of each of these little sectors that we're going to add up to get the area beneath this polar curve? Well, the radius, or the distance from the origin to the curve, is going to be represented by this curve, right? R equals f of theta. The radius of your curve, or the distance from the origin, is determined by this function in terms of theta. So the radius for each of the infinite number of sectors between these two angles would be represented by this function, or would be represented by your polar equation that represents your polar curve. So this r corresponds to this r. And then what about theta? What will theta be for each of our infinite sectors between our two angles? Well, in this case, the angle theta of our sectors is playing the same role as the width of our rectangles, right? As we draw more and more rectangles between these two values of a and b, the width of those rectangles gets infinitely small, and we represent that with dx. In this case, in the polar coordinate system, as we draw more and more sectors between these two angles of theta, the angle of each of the sectors is going to get smaller and smaller. Theta for the sectors is becoming infinitely small. So in this case, we will represent that with d theta. So what we can do to calculate the area beneath a polar curve between two angles of theta is integrate the area of a sector, where we will have 1/2 times r squared times d theta. All right, this will represent the area where the radius r is determined by our function in terms of theta that represents our polar curve, and d theta represents the angle of our sectors that is getting infinitely small as we integrate between alpha and beta to add up the area of an infinite number of sectors. All right, and so this area formula right here, the area equals the integral from alpha to beta, which are two angles of theta, of 1/2 times r squared times d theta, represents the area beneath a polar curve between two angles of theta in the polar coordinate system. All right, and this integral is in terms of theta, just like we said it should be, because r is represented with a function in terms of theta, and d theta, of course, is also in terms of theta. D theta tells us that we are going to be integrating with respect to theta when we calculate our area. Okay, and of course our bounds of integration are also in terms of theta. All right, and so to summarize what we just found, the area under polar curves can be calculated by using this definite integral. The area is equal to 1/2 times the integral from theta equals alpha to theta equals beta of r squared times d theta. Okay, and of course r is represented by a function in terms of theta, and if you wanted to, you could keep this 1/2 inside the integral, but I like to pull it out since it's a constant, and so that's why I have 1/2 times the integral from alpha to beta of r squared d theta. Okay, so now let's take a look at some example problems of using this definite integral to calculate the area under some polar curves. All right, so here's our first example. We want to find the area of the region enclosed by r equals 6 times sine theta. All right, and the first thing that I recommend that you do for these problems when you want to calculate the area inside a polar curve or beneath a polar curve is to draw a sketch of your polar curve. It's going to be very helpful for determining your bounds of integration, right? What two angles of theta you need to integrate between. Now in this case we have r equals 6 times sine theta. That's a pretty simple polar equation that we can sketch a graph of. And if you're not familiar with polar graphing, feel free to check out my previous videos, my lesson and my examples video on polar graphing. That should be helpful for seeing how to quickly graph these polar equations. But in this case, r equals 6 times sine theta just represents a circle with a diameter of 6 that will rest above the polar axis. All right, and so if we go to our polar coordinate system here, if we say that this third circle here represents a radius value of 6, then the graph of our polar equation will look something like this. All right, we just have a circle that rests on top of the polar axis with a diameter of 6, and it's split by the vertical axis. That's how you quickly graph r equals 6 times sine theta. Of course, if that value of 6 was negative, if we had negative 6 times sine theta, then this circle would be flipped to be below the polar axis, but since it's positive, it stays above the polar axis. All right, so this is our polar curve, and we want to find the area of the region enclosed by this curve. So the area that we want to calculate using a definite integral is this area that I'm shading in right now. And so in order to calculate the area, we will use the following definite integral of 1/2 times the integral from some lower bound of theta alpha to an upper bound of theta beta of r squared times d theta. All right, so the easy part is plugging in r. We already know that r is equal to 6 times sine theta, so we can plug that in. The tricky part of these problems is determining your bounds of integration. What two values of theta do we need to integrate between to calculate this area? Now, what I'm always going to recommend when you calculate the area enclosed by polar curves is to take advantage of symmetry when possible. Because when you take advantage of symmetry, it's going to make solving your definite integral a whole lot easier and sometimes a whole lot quicker. All right, so if you look at our polar curve here, notice that it's just a circle, so it's going to be symmetric about this vertical axis, right? The curve is the same on this side of the axis as it is on this side. So when we calculate the area, what we can do is just calculate the area of half of the circle and then multiply the definite integral by 2. We can double the area of half that circle to get the full area of the circle. All right, so what we're really going to do is just represent the area of 1/2 of this circle and then multiply it by 2. And so what two angles does this area lie between? Well, when our angle is 0, typically that's where we like to start. If you plug in an angle of 0 into your polar equation, sine of 0 is 0 and 0 times 6 is 0, so the radius is 0 when the angle is 0. That tells us that we're starting at this point right here, which is the origin. And so then what we know is that this area of the circle is going to be between this angle of 0 and this angle of pi divided by 2. All right, the curve that this area is beneath starts at the angle of 0 and stops at the angle of pi divided by 2. Okay, so here's what we're going to have. Our area will be equal to 1/2 times the integral from 0 to pi divided by 2 of r squared, which will be 6 times sine theta squared times d theta. All right, this represents the area of 1/2 of our circle. But in order to calculate the whole area of the circle, we need to multiply this definite integral by 2. So the area will actually be equal to 2 times that definite integral. All right, and so that will make calculating our area hopefully a little bit easier. Of course, your bounds of integration could be from 0 to pi, right? This whole area lies between the angles of 0 and pi. You could go about it that way, but I like to take advantage of symmetry if at all possible. All right, because what's going to happen here is this 2 and this 1/2, they're going to cancel each other out. 2 times 1/2 is 1. So I'm just going to cross that out. And what we'll have is that this is equal to the integral from 0 to pi divided by 2 of 6 times sine theta squared. So if we square each part, 6 squared is 36, and sine theta squared is sine squared theta. So we'll have 36 times sine squared theta d theta. Okay, and so now we have set up our definite integral. Now all we have to do is solve it to find the area enclosed by this polar curve. And the first thing I'm going to do to solve this integral is pull 36 to the outside. Since it's a constant multiple, we don't need to have that inside the integral. It'll be easier to work with if we pull it to the outside. So this will be equal to 36 times the integral from 0 to pi divided by 2 of sine squared theta. Now, what I'm going to do is rewrite sine squared theta into a form that we can actually integrate, because in its current state, sine squared theta is not easily integrated. And so this is where your skills of solving trigonometric integrals come into play. We covered the topic of solving trigonometric integrals earlier in Calculus 2. That was one of our advanced integration techniques that we learned. And so if you need a refresher, feel free to go back to that video, because what's going to happen with these integrals for calculating area beneath polar curves is that they're pretty much all going to be trigonometric integrals that you need to know how to solve. All right, so in this case, when we have sine squared theta, what we do is we rewrite that by using a trig identity. Specifically, we use a trig identity that sine squared theta is equal to 1/2 times 1 minus cosine of 2 theta. All right, and so that's what we're going to replace sine squared theta with, and then don't forget d theta. Okay, so now that we have replaced sine squared theta with 1/2 times 1 minus cosine of 2 theta, solving this integral should be a whole lot easier. First thing I'm going to do is pull this 1/2 to the outside. 36 times 1/2 is 18. So this is equal to 18 times the integral from 0 to pi divided by 2 of 1 minus cosine of 2 theta d theta. All right, and now what I'm going to do is split up this definite integral into two parts. We'll integrate each of these terms individually. So we'll integrate 1, and then we'll integrate cosine of 2 theta. So we'll write it like this. This will be equal to 18 times the integral from 0 to pi divided by 2 of 1 times d theta minus, right, we have a minus sign here, 18 times the integral from 0 to pi divided by 2 of cosine of 2 theta d theta. Now the reason I split this up into two integrals is because to integrate cosine of 2 theta, we're going to need to use u substitution, so it makes sense to split up those two terms into two integrals so that we can integrate them separately using the different techniques that they will require in order to be solved. All right, so now let's work on solving each of these integrals. This first integral is going to be pretty easy. The integral of 1 is just going to be theta, right? When you integrate a constant, the integral of that is just going to be that constant multiplied by the variable of integration, which in this case is theta, right? We're integrating with respect to theta. That's what d theta tells us. So this will be equal to 18 times theta evaluated from 0 to pi divided by 2. And then for our second integral here, we need to use u substitution because we have cosine of 2 theta. If we just had cosine of theta, this would be a pretty easy integral to solve. In fact, it's still pretty easy, but we do need to use u substitution because we have a function other than just theta within cosine. All right, so we're going to set u equal to that inside function. So I'll write this work on the side here. We're going to let u equal 2 theta, which means that du d theta, the derivative of u with respect to theta, will be equal to 2. And then if we solve for du by multiplying both sides by d theta, we'll have du is equal to 2 times d theta. Now I don't see 2 d theta in our integral, right? Whatever du is equal to needs to be found in our integral. I just see d theta, so I'm going to divide both sides of this equation by 2, and we'll have du divided by 2 is equal to d theta. All right, that's what that equation will give us. Now we can replace d theta with du divided by 2. All right, so what we'll have for this integral is minus 18 times the integral from theta equals 0 to theta equals pi divided by 2 of cosine of u times du divided by 2. All right, and I wrote our bounds of integration as theta equals pi divided by 2 and theta equals 0 because those are still in terms of theta, but the rest of our integral is in terms of u. I don't want you to forget that those are values of theta. But we can change them to be values of u, and we'll do that in our next step. But before we work on that, let's work on evaluating theta here. This will be equal to 18 times theta evaluated at pi divided by 2 minus theta evaluated at 0. That's just going to be pi divided by 2 minus 0, which is just going to be pi divided by 2. All right, so then we'll subtract our next integral, and I'm going to pull this 1/2 that's being multiplied by du out to the front. So we'll have 18 times 1/2, which is 9. So we'll subtract 9, and then integrate between our two bounds of integration, which I'm going to change to be in terms of u. That way we don't have to integrate and then go back into terms of theta. We can just work in terms of u. And we can do that by plugging these angles of theta into what we set u equal to. So when theta equals 0, we'll have 0 times 2, and that will be 0. So u equals 0 when theta is 0. So our new lower bound is u equals 0. And then our upper bound of theta equals pi divided by 2. Pi divided by 2 times 2 will be pi. So our new upper bound will be u equals pi. All right, so we'll have u equals pi. And then we still have cosine of u times du. All right, so now we can integrate this pretty easily. The integral of cosine is sine. So this will be equal to 18 times pi divided by 2. 18 divided by 2 is 9, so that will be 9 pi. and then we will subtract 9 times the integral of cosine, which is sine. So we'll have sine u evaluated from 0 to pi. Now here's where things get interesting, because if we evaluate sine at pi and then subtract the evaluation at 0, sine of pi and sine of 0 are both 0. So we have 0 minus 0, which makes this whole value 0. And so 0 times 9 is 0. So we're just subtracting 0 from 9 pi. So this whole term becomes 0. And our final answer is that the area is equal to just 9 pi. That is the area of this region enclosed by this polar equation. Okay, so that's how you can calculate the area of a region enclosed by a polar curve. In this case, we were working with a circle, so there is actually an easier way to find this area without integrating, right? If this circle has a diameter of 6, then it has a radius of 3, and we know that the area of a circle is pi r squared, so 3 squared is 9 times pi is 9 pi. So that's a lot easier of a way to calculate the area of this circle, but that's not the point of this video. The point of this video is to show you how to use a definite integral to calculate the area beneath a polar curve. All right, so while this process really wasn't that necessary to calculate the area inside this circle, there are going to be more complicated polar graphs where using a definite integral to calculate the area is going to be necessary. And so let's take a look at another example. All right, so here's our next example. We want to find the area of the region enclosed by r equals 1 plus cosine theta. All right, so unlike our previous example, this polar equation is not going to represent a circle. In fact, if you are familiar with your polar equations and their graphs, you might recognize this equation to be a cardioid, right? This specific polar equation is in the form of r equals some constant plus another constant times cosine theta. In this case, both of those constants are 1. Right, the general form of this type of polar equation is r equals a plus or minus b times cosine theta, and this is the general form of a limison. Specifically in our case, a is equal to 1 and b is equal to 1, and to determine what type of limison you have, you take a and divide it by b, and depending on that value, you'll have a different type of limison, which determines what your graph will look like. In this case, a divided by b is 1 divided by 1, which is equal to 1, and when a divided by b is equal to 1, you know you have a cardioid, which is a heart shape. Specifically, when you have the cosine function in this equation and not sine, your cardioid will be shaped like this. You'll have a cardioid or a heart that is oriented in this direction. All right, so that's the basic idea of what this graph is going to look like, but let's sketch it a little bit more accurately in this polar coordinate system here. We can quickly sketch the graph by using our values of a and b. The back end of this cardioid will be the radius value of a plus b, so 1 plus 1 is 2. So if we say that our fourth circle here is a radius of 2, I'm going to say that that's a radius of 2, and the second circle is a radius of 1, then the back end of our cardioid will pass through that point there, and then this point and this point, that's going to be the radius value of a, which is 1. So this second circle is a radius of 1 in both directions, so our cardioid is going to pass through this point and this point. Okay? And so then we can use those 3 points to draw our cardioid. We'll start at the back end, come through this point, meet at the origin, come back out, pass through this point, and come back to the back end. All right, so this is the polar curve represented by this polar equation. Now we can see that the area that we want to calculate that is enclosed by this region will be this area right in here. And as you can see this time, this is a much more complicated area to calculate. It's not just a circle, so we're going to need to use a definite integral. All right, so the area will be equal to 1/2 times the integral from alpha to beta of r squared d theta. In this case, r is equal to 1 plus cosine theta. That's the easy part. But what about our angles of theta? What two angles does this area lie between? Well, the full shape of a cardioid would be from an angle of 0 all the way around to 2 pi, right? This whole area is enclosed between 0 and 2 pi. But just like with our previous example, I always recommend that you make use of symmetry when possible. And you can notice that with this shape, this cardioid shape is symmetric about the polar axis, right? It's the same above the polar axis as it is below. So instead of integrating from 0 to 2 pi, we can just integrate from 0 to pi and multiply the definite integral by 2. We'll calculate the area of half of the cardioid and then multiply it by 2 to get the area of the full cardioid. So here's what we'll have. The area will be equal to 2, that's our 2 that we're using to double the area, times 1/2 times the integral from 0 to pi of our radius squared. So we'll have 1 plus cosine theta squared times d theta. All right, this definite integral will represent the area of this cardioid. We're integrating from 0 to pi, which will be half of the shape, but then we're multiplying it by 2 to get the full area. Okay, so now let's work on solving this definite integral to calculate our area. First thing that I notice is that 2 times 1/2 is just going to be 1, so those are going to cancel out. So the area will be equal to the integral from 0 to pi of this quantity squared. And so we're going to want to expand that. We're going to want to square this quantity. And the easiest way to do that is to square the first term. So 1 squared is 1. So we'll have 1 plus these two terms multiplied together and then multiplied by 2. 1 times cosine theta is cosine theta, and then multiplied by 2 will be 2 cosine theta, and then we will square the last term. So we'll have plus cosine squared theta. And then don't forget d theta. All right, so now we have 3 separate terms that we need to integrate. 2 of them are pretty simple, right? 1 and 2 times cosine theta are pretty easy to integrate, but cosine squared theta is not as easy. We're going to need to use a technique from solving trig integrals in order to integrate that term. So what I'm going to do is split up this integral into 3 integrals, one for each of our terms. So this will be equal to the integral from 0 to pi of 1 d theta plus the integral from 0 to pi of 2 times cosine theta d theta plus the integral from 0 to pi of cosine squared theta d theta. All right, and now we can integrate these 2 terms pretty quickly and then work on integrating cosine squared theta separately. Okay, so the integral of 1 is theta. So this is equal to theta evaluated from 0 to pi, and then we'll add that to the integral of 2 times cosine theta. The integral of cosine is sine, so we'll have 2 times sine theta evaluated from 0 to pi. And then we'll add that to this integral, but in order to integrate cosine squared theta, just like with sine squared theta in the previous example, we need to rewrite it using a trig identity. In this case, our trig identity is going to look slightly different. For cosine squared theta, we will rewrite it as 1/2 times 1 plus cosine of 2 theta. All right, so now let's simplify. Let's evaluate theta at pi and subtract the evaluation at 0. That's just going to be pi minus 0. So this is equal to pi. And then we'll add that to 2 times sine theta evaluated at pi, and then subtracting the evaluation at 0. However, sine of pi and sine of 0 are both 0, so we're just subtracting 0 from itself, and so this whole term just becomes 0. All right, so we would be adding 0 to pi, but we don't really need to write that. We can just move on to our next integral, which we're going to work on next. And I'm going to pull this 1/2 to the outside, so we'll have 1/2 times the integral from 0 to pi of 1 plus cosine of 2 theta. All right, now in order to solve this integral, I'm going to split it up into 2 integrals, one for this term of 1 and one for this term, because once again, cosine of 2 theta is going to require using u substitution, just like we did in the previous example. So we'll have that this is equal to pi plus 1/2 times the integral from 0 to pi of 1 d theta plus 1/2 times the integral from 0 to pi of cosine of 2 theta d theta. All right, so now let's work on integrating these 2 integrals to finalize our answer for the area within this polar curve. All right, so let's start by integrating this integral. That'll be pretty easy. This is equal to pi plus 1/2 times the integral of 1, which is just going to be theta. So we'll have theta evaluated from 0 to pi. All right, and then this is added to 1/2 times the integral from theta equals 0 to theta equals pi. And now I'm going to rewrite this using u substitution. We're going to do the exact same u substitution process that we used in the previous example. Since we have cosine of 2 theta, we need to set u equal to that inside function, and then we'll be able to integrate. All right, so once again, let's do our side work over here. U is equal to 2 theta, which means that du d theta, the derivative of u with respect to theta, will be 2, which means that du is equal to 2 times d theta if we multiply both sides of the equation by d theta. Now, we don't have 2 d theta in our integral, so we need to divide both sides by 2 so that whatever our term in du is equal to, we can find in our integral. So we'll do that. If we divide both sides by 2, du divided by 2 is equal to d theta. So now we can replace d theta with du divided by 2. So we'll have cosine of u times du divided by 2. All right, and once again, our bounds of integration are in terms of theta right now, but we're going to switch them to be in terms of u in our next step. And so let's work on that. Our next step is that this is equal to pi plus 1/2 times theta evaluated at pi minus theta evaluated at 0. That's just going to be pi minus 0, which is pi. So we have 1/2 times pi. Okay, and then we'll add this to this integral. We'll pull this 1/2 out to the front, so we'll have 1/2 times 1/2, which will be 1/4 times the integral from 0 to pi in terms of theta, but now we're working in terms of u. And so let's plug these bounds of integration into what we set u equal to. For 0, we'll have 2 times 0, which is 0, so the lower bound will be u equals 0. And then the upper bound of pi, we'll plug that in, and we'll have 2 times pi, so u is equal to 2 pi. So our upper bound is u equals 2 pi. And then we have cosine u times du. All right, now if we integrate that, the integral of cosine is sine. So this is equal to pi plus 1/2 times pi, which is pi divided by 2, plus 1/4 times sine u evaluated from 0 to 2 pi. All right, and now to simplify, sine of 2 pi is 0, sine of 0 is 0, so this whole term is just going to become 0. So we'll cross this out, that is 0, so our final answer is that the area is equal to pi plus pi divided by 2, and pi plus pi divided by 2 is 3 pi divided by 2. That is going to be the area of the region enclosed by this polar curve. Okay, let's take a look at one more example of calculating the area beneath a polar curve. All right, so here's our last example. We want to find the area of the region enclosed by one petal of the rose curve represented by r equals 3 times cosine of 3 theta. All right, now in this case, our prompt kind of gives away what the graph of this polar equation is. We're told that we want to find the area of a petal of the rose curve represented by this polar equation. So we know we're working with a rose curve. This polar equation is in the right form to represent a rose curve. In this case, we're going to have a rose curve dealing with cosine, which is a lot easier to graph than rose curves dealing with sine. All right, but the values that you want to pay attention to in this polar equation are the two constants that you see. The constant in front of the cosine function and the constant being multiplied by theta. The constant on the outside tells you the value of the radius that each petal of the rose curve will reach out to, and the constant multiplied by theta is going to tell you how many petals you will have in your rose curve. When that constant is odd, you're going to have that number of petals, but if it's even, you multiply that value by 2 to determine how many petals you have. So in this case, 3 is an odd number, and so we know that we're going to have 3 petals in this rose curve. All right, so we're going to have 3 petals, and each petal is going to reach out to a radius of 3. That's what this polar equation tells us. Now, in order to graph a rose curve dealing with cosine, at least when your constant in the front is positive, you start by drawing one petal along the angle of 0. Okay, if your constant in the front was negative, you would start on the other side along the angle of pi. But in this case, 3 is positive, so we're going to draw our first petal along the angle of 0. In this case, the petal is going to reach out to a radius of 3. So if we count 3 circles, 1, 2, 3, we're going to go out to this circle right here. I'm going to say that that is where the radius is 3. So one of our petals will look like this. And then we need 2 more petals because we need to have a total of 3 according to this value in front of our angle. And so we just have to distribute the other 2 petals evenly. So we'll have 1 over here and 1 over here. Okay, this is not a perfect sketch of the graph, but this is the basic idea. This is essentially how the graph of the rose curve for this polar equation will look. In fact, we didn't really need to even draw the other 2 petals. We only really needed to work with 1 because we want to find the area of the region enclosed by 1 petal of the rose curve, not all 3 petals. And so the area that we want to calculate in this case is this area right here inside 1 of the petals. All right, and so in order to calculate this area, we need to use a definite integral that the area is equal to 1/2 times the integral from alpha to beta, or 2 values of theta that the area lies between, of r squared times d theta. All right, now we know r is equal to 3 times cosine of 3 theta. That's pretty easy. What's a little bit more tricky to determine are the bounds of integration. what two angles of theta does our region lie between? And in this case, that's not really obvious. It's not really easy to just look at this petal and determine what angles it's between. You might be tempted to say that, well, it's between 3 pi divided by 2 and pi divided by 2 because it starts here and comes back around, but that's not really going to be correct, especially because this polar equation includes cosine of 3 times theta. That constant multiple being multiplied by theta is going to make it a lot more difficult to just look at your graph and determine visually what angles the region lies between. So instead of doing it that way, here's what I recommend that we do instead. In order to determine what values of theta we're going to be between for this region, we just have to figure out when this rose curve is at the pole, right? When does this curve come in and cross through the origin? Because if you notice, this petal is enclosed by a curve that starts at the origin and wraps around and comes back to the origin. So if we set our polar equation equal to 0, right, when r is equal to 0, we can solve for the angles where the curve is at a radius of 0, when it's at the pole. So if we do that, we'll let 0 equal 3 times cosine of 3 theta. We can solve for theta by first dividing both sides by 3. 0 divided by 3 is 0. So we'll have 0 is equal to cosine of 3 theta. And then this is where it gets a little bit tricky. When does cosine of 3 theta equal 0? Well, we know that cosine of pi divided by 2 and 3 pi divided by 2 is equal to 0. And so we just have to determine what value of theta would make this whole angle within cosine equal to pi divided by 2 or 3 pi divided by 2. So all we have to do is set 3 theta equal to those two angles. So we'll have 3 theta is equal to pi divided by 2, and 3 theta is equal to 3 pi divided by 2. And now we just have to solve for theta. All right, so if we do that, we'll divide both sides of these equations by 3. That will solve for theta. And so we'll have theta is equal to pi divided by 6, right? If we divide both sides by 3, you'll have 2 times 3 in the denominator here. So we'll have theta equals pi divided by 6, and theta equals 3 pi divided by 6. And that will reduce to pi divided by 2, right? We could reduce the numerator and denominator by a factor of 3 to get pi divided by 2. So I'll just erase this, and we'll have pi divided by 2. Okay, so with these two angles, we know for a fact that our rose curve is going to be at the pole, at the origin. Now what we're going to do here is just use the smaller angle. That's telling us the first time that our rose curve touches the pole. All right, because if you plug in an angle of 0 into this polar equation, 3 times 0 is 0, and cosine of 0 is 1, so you have 1 times 3. So the radius is 3 when the angle is 0. So when the angle is 0, we're at this point right here where the radius is 3. This is where our curve starts. And then what we learned from this angle is that at pi divided by 6, we're going to be at the pole. So if we're starting at this point at theta equals 0, then the next angle of pi divided by 6, that's smaller than pi divided by 2, this angle will take us to this point right here. Okay, so from here to here, we go from theta equals 0 to theta equals pi divided by 6. And so this angle that bounds our region above is the angle of pi divided by 6. And then since this petal is symmetric about the polar axis, we can say that the angle below it would be negative pi divided by 6. And that would be the same as 11 pi divided by 6, but negative pi divided by 6 is easier to work with, but we're actually not going to work with it, and I'll show you why in just a second. But now what we know is that this region, this area inside this petal of this rose curve, lies between the angles of pi divided by 6 and negative pi divided by 6. So we can set up our definite integral like this. We'll have that the area is equal to 1/2 times the integral from negative pi divided by 6 to pi divided by 6 of r squared, and r is equal to 3 times cosine of 3 theta. So we'll have 3 times cosine of 3 theta squared, and then if I erase this work, we can write d theta. Okay, so this is one way that we could calculate that area. But like I've said in the previous two examples, you should always try to take advantage of symmetry if you can, because it will make your integration process a lot easier. In this case, we know that this petal is symmetric about this polar axis. So we can just integrate from 0 to pi divided by 6, and then multiply the area by 2. We'll calculate the area of half of this petal, and then multiply it by 2 to get the area of the full petal. All right, so instead of writing our area like this, I'm going to write it like this. We'll have that the area is equal to 2 times 1/2 times the integral from 0 to pi divided by 6 of this quantity squared. So we'll square 3 and square cosine of 3 theta. So we'll have 3 squared, which is 9, times cosine squared of 3 theta d theta. All right, so this is the definite integral that we will use to calculate the area of this one petal of this rose curve. So now let's work on solving this integral. And the first thing that I noticed that we can do to solve this integral is cross out 2 times 1/2, because 2 times 1/2 is just 1, so they cancel each other out. And then we can pull this 9 to the outside of the integral, since it's a constant multiple. So this will be equal to 9 times the integral from 0 to pi divided by 6 of cosine squared of 3 theta d theta. All right, and then this integral in its current state, we can't really solve. We need to rewrite cosine squared of 3 theta in some way so that we can integrate it. And so we're going to use the same trig identity that we used before. We're going to use the identity that cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta. But what's important to realize in this case is that since our original angle is 3 theta, we're going to have 2 times 3 theta when we rewrite this, all right? It's not just cosine squared of theta like we have here, it's cosine squared of 3 theta. So we'll have 3 theta times 2. All right, so just keep that in mind. So what we're going to have is that this is equal to 9 times the integral from 0 to pi divided by 6 of 1/2 times 1 plus cosine of 2 times 3 theta d theta. Okay? Now the next thing that we can do is pull this 1/2 to the outside. 9 times 1/2 is 9/2. So this is equal to 9/2 times the integral from 0 to pi divided by 6 of 1 plus cosine of 2 times 3 theta. 2 times 3 is 6, so we'll have 6 theta d theta. Okay? So now what we're going to do is split up this definite integral into 2 integrals, one for this term and one for this term, because in order to integrate cosine of 6 theta, just like cosine of 2 theta, we need to use u substitution. Because we have cosine of some function other than just theta, we need to use u substitution, where we set u equal to that inside function. All right, so let's work through that. This will be equal to 9/2 times the integral from 0 to pi divided by 6 of 1 times d theta plus 9/2 times the integral from 0 to pi divided by 6 of cosine of 6 theta d theta. All right, so now let's work on integrating this integral and using u substitution on this integral. The integral of 1 is just theta, so this will be equal to 9/2 times theta evaluated from 0 to pi divided by 6, and then we'll add this to 9/2 times the integral from theta equals 0 to theta equals pi divided by 6. Now I wrote our bounds of integration like that because now we're going to rewrite the rest of our integral in terms of u, and I want you to remember that these bounds of integration are still values of theta. All right, so now let's work on that u substitution process. We're going to set u equal to 6 theta. So we'll have u equal to 6 theta, which means that du d theta, the derivative of u with respect to theta, is equal to 6. And so if we multiply both sides by d theta, we'll have that du is equal to 6 d theta, but I don't see 6 d theta in our integral. So if we divide both sides by 6, we'll have du divided by 6 is equal to d theta, and now we have a term of du that is equal to d theta, which we can find in our integral. So if we use our u substitution process, we'll have cosine of u times du divided by 6. All right, now if we simplify, we'll start with this integral. Theta evaluated at pi divided by 6 is pi divided by 6, and then we're subtracting theta evaluated at 0. So we have pi divided by 6 minus 0, which is just pi divided by 6. So this is equal to 9/2 times pi divided by 6, and then we'll add that to this integral, but I'm going to pull 1/6 out to the front. So we'll have 9/2 times 1/6 times the integral from theta equals 0 to theta equals pi divided by 6 of cosine of u times du. Now let's rewrite these bounds of integration from being in terms of theta to being in terms of u. So we'll plug each of these values into what we set u equal to. Theta equals 0 will give us 0 times 6, so u will be equal to 0. So that lower bound will stay 0, but now it's u equals 0 instead of theta. And then the upper bound of pi divided by 6, if we plug that in, pi divided by 6 times 6 will be pi. So u is equal to pi for the upper bound. So I'll rewrite that to be u equals pi. Okay, now our integral is entirely in terms of u, so we don't have to worry about going back into terms of theta. We can just integrate cosine and then evaluate. Alright, so now if we simplify, 9 halves times pi divided by 6 will be equal to 9 pi divided by 12, right? 9 times pi is 9 pi, and 2 times 6 is 12. And then we'll add that to 9 halves times 1/6, that will be 9 divided by 12, times the integral of cosine u, which will be sine u. The integral of cosine is sine, and that's evaluated from 0 to pi. But now sine of pi and sine of 0 are both equal to 0, so this will evaluate to be 0 minus 0. So this whole thing will be 0 times 9/12, which will just become 0. So we're just going to be left with 9 pi divided by 12, which does simplify. 9 and 12 can be reduced by a factor of 3, and if we do that, we'll find that the area is equal to 3 pi divided by 4. 3 pi divided by 4 is the area of one petal of the rose curve represented by this polar equation. Okay, so hopefully that process made sense. When you're not sure what the angles will be for some more complicated shapes within the polar coordinate system, you just want to try to locate those angles where the polar curve is going to hit the pole. That will help you determine what those values of theta will be. So you just want to set your polar equation equal to 0 and solve for theta. All right, so that's really the hardest part of these problems, because by this point solving definite integrals is not a new concept. The hardest part here is just determining what those angles of theta will be for the region that you want to calculate the area of. All right, and so with that, this was the last example for this video, but if you want to see some more examples of calculating area under polar curves, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.